Hello and welcome back to this brief video series on applications of exponential functions. In the second video, we are going to examine some finance applications, and we're going to start with compound interest. Now, the formula for compound interest is A equal to P times the quantity 1 plus R over N, and that quantity is raised to the NT power. So A is the future amount, P is the present amount, N is the number of compounding periods per year, T is the number of years, and R is the rate. Now, when we use this formula, we convert the rate into a decimal. So if you wanted to use this formula, compound interest formulas are used when you put in a lump sum payment and you just let it accumulate interest over time. Now, the reason why it's called compound interest is because this kind of account may be used to not only build interest on what you put into the account, but it also builds interest on what interest you've already previously accumulated. So it's not like simple interest where it only builds interest on the amount you are depositing. Compound interest builds interest on the amount you deposited plus any previously earned interest. And this is why it's called compounding. Now, another formula associated with compound interest is the effective rate. And the effective rate is commonly used to determine what simple interest rate is needed to match the compounding interest rate over a year. So the effective rate may be calculated as the quantity 1 plus R over N raised to the N power. And then we take that result and subtract 1 from it. Now, the reason why we have effective rate is that this is useful when you're comparing different interest rates. So, for example, if you had some student loans and they were offering you different interest rates, you could use this formula to determine which interest rate would be the least, because it levels the playing field, so to speak, by saying this is the simple interest rate that you would have if you were just paying interest on the amount that you were borrowing. So if you're borrowing money, if you're taking a student loan, for example, then you would want the effective rate that was the lowest, because that would imply that you would be paying the least amount of interest on the amount you're borrowing. Remember, the amount you borrow is going to be the same regardless of which institution you borrow from. It's the interest that could be different, and this formula kind of levels that playing field, telling you this is how much interest, this is what the interest rate, I should say, would be if it were simple interest rate. And then this will help you decide which one would be, quote unquote, the best loan for you. Some other applications with exponential functions include the annuities. Now, annuities are regularly scheduled payments. Now, you can have a regularly scheduled payment made at the end of a period, and that is the ordinary annuity. So the formula for the ordinary annuity is capital S, which is the total sum in the account, is equal to capital R, which is the regularly scheduled payment, the amount of money you're putting into this account regularly. And that capital R, that regularly scheduled payment, is going to multiply this ratio. And the ratio is 1 plus R over N, all of that raised to the NT power minus 1. That's the numerator part of that ratio. Then you're going to divide that by R over N, where little r, little n, and little t all mean the same thing they did in the compound interest formula. Little r is the interest rate that's usually given to you as a percent, so make sure you convert it to a decimal before you use this formula. Little n represents the number of compounding periods per year, and little t represents the time in years. So the ordinary annuity is the formula or the calculation that you would use if you are making payments at the end of a period. And this is pretty common in finance applications. The annuity due is when you make regularly scheduled payments at the beginning of a payment period. And rent is usually the prime example for this, because you normally pay rent at the beginning of a month. And then if you decide to leave, they may prorate it based on the amount of time left on the lease. They may give you some money back. Again, that would be written out in the contract for that particular establishment. Now, the ordinary annuity and the annuity due have very similar formulas. The difference between them is that the annuity due has the ordinary annuity formula in there times this quantity, 1 plus R over N. And that extra factor is here because when you make payments at the beginning of a period, you're still earning interest to the end of that term, the end of the loan's term, the maturity, if you will. So you made a payment at the beginning of the period, and you're still going to earn a little bit of interest during that last payment period. And that's why that extra factor is there on the annuity due. So the annuity due has that extra factor because you pay at the beginning of the period, where ordinary annuities are made at the end. The payments are made at the end of the period. So let's see an application. Suppose you wish to have $5 million when you retire, and there are many factors that are involved in such a goal. We'll go ahead and consider these items: the age of the person, the age of retirement, the rates of growth, and the amount of money available to place into an account. So if we consider a situation like mine, let's consider an age of being 50. Let's say that the person is going to retire at 70. Let's say that the current interest rate on average is about 4.02%, and this comes from the Edward Jones money market funds rate. And so what we're trying to do is we're going to determine how much I would need to invest each month to reach a $5 million goal. So using the ordinary annuity formula, because otherwise stated, if it doesn't say it makes payments at the beginning of the period, then we assume an ordinary annuity. We put our numbers into that formula, we do the calculations, and we end up with roughly $13,602 per month to reach the investment goal of $5 million when I retire in 20 years. So pause this video, using the same situation, see how much money you would need to deposit into an account if you choose to retire at the age of 70. Another application that's related to annuities are the mortgage payments. Now, mortgages are loans given out by banks in order to acquire real estate. And the formula for figuring out the mortgage payment, now this does not include PMI or escrow or insurance or anything like that. It's just strictly focused on the loan made by the bank for this mortgage. The formula happens to be R. That capital R, again, means the amount that you're going to pay for the loan, is equal to capital A, that's the amount of the loan itself, times the quantity R over N. And that product is going to be divided by 1 minus the quantity 1 plus R over N raised to the negative NT power. So this formula is what's used to calculate payments on a mortgage, if you will. Now on this slide, we have two graphs, and we'll describe what these graphs are in just a moment. But suppose you're buying a home and you set up a mortgage of $100,000 at 5.2% interest, compounded monthly for 30 years. Now the graph on the right, the first graph at the top on the right, will show the balance decreasing over time. Now the monthly payment under these conditions is $549.11. I encourage you to use that formula on the previous slide and calculate this. Now the graph here says that T equals 10, X equals 10, and then Y equals $98,819 and about 38 or 39 cents. So what this is saying is that after 10 payments, you have paid $1,181 toward the balance of the loan. The rest of that money has gone toward interest. So if you take $549.11 and multiply that by 10, because that's the number of payments, you get $5,491.10. That's how much you've paid toward the loan. But only $1,181 actually went toward the principal. The other $4,310.10 actually went toward interest on the loan. Okay? So, and this is how mortgages work, because remember, the bank is loaning you money for a very long period of time. So they are taking on a lot of risk. So you're going to pay for the interest right up front for having to borrow this money. Now, the graph on the bottom here shows what would happen if you made 180 payments. Now, after 180 payments on this loan, the amount that you still owe is $68,531 and about 68 cents. You've paid just over $30,000 toward the actual loan amount. You still have a lot of interest that you're paying on. So for this mortgage scenario, it is actually at the 201st payment that the portion of the principal actually overtakes the interest on the loan, and that's shown here in the chart. So the amount of interest I pay on the 201st payment is $274 and about 20 cents. The portion of the principal is actually $274 and about 92 cents. So it's at this point that you're finally making what would be considered a huge dent in your actual loan. All right, it's not up to this point that you're still paying more on interest than you're actually paying toward the principal. So amortization schedules are given out by banks to let you know all of this information. Okay. So hopefully these little demonstrations here will help you understand some certain aspects of finances and the models, the exponential models that are involved with it. So on the third and final video for this series, we are going to examine Newton's law of cooling, and this is where the third video will pick up. So I look forward to seeing you back here again for our third and final video, and I hope you enjoyed it, and thank you for your time and attention.